Thank you. So, okay. Yes.
Good afternoon. Good afternoon, everyone. My name is Amir Meshurer. I'm a PhD student in industrial engineering at Ben-Gurion University in Beersheba, Israel. And today I will present our paper called Comparative Analysis of Cameras and Software Tools for Skeleton Tracking, published in IEEE Sensor in 2024. First, to understand skeleton tracking, we need to talk about motion capture. Motion capture is a process of tracking and recording the movement of an object. It's used in a variety of fields, such as rehabilitation, physical training, movies or animation, video games, and sports analysis. Skeleton tracking is one type of motion capture. And it means that it's tracking a human's body movement by identifying the location of specific joints, such as the head, shoulders, elbows, and knees, as can be seen in the figure here below. Mostly, skeleton tracking technologies are divided to two marker-based systems, such as a Vicon motion system, which means that we are locating markers on the subject body and the exact location of the joints, and we track the markers location using specific technologies. In the Vicon motion system, we use infrared cameras to locate the joint's location. Those systems are very accurate, but lab restricted. They are complex to set up and expensive. And the second skeleton tracking technologies are markerless video-based systems, which are cheap technologies that can be used widely and they use a variety of technologies. And the skeleton tracking algorithms are the algorithms that use those technologies and they are returning to us the locations of the joints over frames, over time. For example, the algorithms we used in our paper are the Nuitrack, MediaPipe, PyZED, with their pros and cons. And there are a lot of them in the media. So we have several cameras and we have several algorithms. And we want to know which combination is the most suitable and perform the best for our purpose, research purpose. So how can we evaluate their performance? The first thought is to take each combination and do a direct joint comparison. Compare the same joint from each camera and algorithm combination with some ground truth systems, such as marker-based systems. But there's two problems. First of all, the skeleton joints may vary between the different algorithms, meaning the same location for the right shoulder can vary between different algorithms. And the second, most importantly one, that the different cameras may have different sampling rates, and it's hard to synchronize them on the same time. So direct joint-to-joint comparison is not feasible, and for the reason I said before. So we have a problem with synchronization of all of them to make a good comparison and to evaluate which combination is suitable for us. So our goal is to define evaluation method that avoids strict synchronization while ensuring fair comparison. Our study objectives divided into two. The first one is to propose a systematic methodology for comparing cameras and skeleton tools without the need for synchronization. And the second is to demonstrate a case study that we did. So our methodology is three-step way methodology. The first one is experimental design, then the features extraction, and at last the feature analysis. The first, in the experimental design, we'll perform an experiment where we take subjects, and for each subject, we perform experiment with different combination of camera and algorithm. And each subject will repeat it using one combination of camera and algorithm, and every time we compare it to the ground truth system. We will use random order for each subject with the different camera and algorithm combination to avoid bias. The second, the feature extraction, we first transform and standardize the data. Since each camera and algorithm are returning different data, so we scale all of them to the ground truth scale, let's say for example meters. We rotate the axes and we shift the origin. Second, we can calculate movement features without depending on accurate synchronization, meaning we'll calculate features that are not dependent on time. That's why we could evaluate them and compare between two different systems. And in the feature analysis, after we calculated all the features, now we can evaluate the performance by comparing the features. How we will do so? So we are using two metrics. The first one is RMSE for comparing between two different sensors. Which one is better? And the second is the linear mixed model for statistical validity. And we are using the mixed model because each subject is doing repeated trials, and we want to take into account the subject variety, variance. In our comparative analysis, we focused on two research focuses. So the first one is the upper body, focusing on the hands movement, and the second is the lower body, focusing mostly on the knee. And we tested three cameras, the Z2i from Stereo Labs, which we used two different lenses, the 2mm and the 4mm, and RealSense camera from Intel. We use three skeleton tracking, the PyZED, which integrate with the Z camera, and Nuitrack and MediaPipe that are used with the RealSense. And each combination is compared to our ground truth, the Vicon motion system, which is a gold standard. In our experiment, we recruited 16 participants, half male, half female, between the ages of 21 to 29. Each participant was asked to walk 6-meter narrow path while moving their hands up and down. We can see here on the image below the top view of the experiment, where the subject begins here in the middle, and he walks to the camera positioned here on the left, the RealSense and the Z cameras, and walking to and from. The circle represents all the cameras of the Vicon motion system as the ground truth. The next video will present a part of the explanation video we showed to the subject what to do in the experiment. So we can see that, it's not working. Oh. The participant beginning by jumping, we can see all the Vicon motion system cameras here and the position camera here. We can see even the marker on the subject body. So after we've done all the experiment, we want to calculate the features. Since we are divided to two research focus, the upper body, most feature here are focused on the upper body on the hands, like the count of horizontal hands movement, the distance from the cameras using the shoulder joint. For the lower body, we calculated the steps calculation, steps length and height, and some of the features are common for both of them. Some of them are the same features, but using different joint. In our feature analysis, as I explained before, we're divided into two parts, the RMSE, and I will explain it now, and the linear mixed model. In the RMSE analysis, we calculate the RMSE value for each camera, for each feature, for all the trials, meaning that we are gaining for each feature and for each camera an RMSE value. And since each feature has different scale, we need to use scaling techniques to bring them all to the same scale. And once we scale them, we sum all the scaled values for each camera. And at last, we can add weighted importance features that we can give different importance for different features depending on our research focus. So the first scaling technique we used, we called it basic normalization. Let's say, for example, for specific feature, we gain the next RMSE values for the next camera. The basic normalization is an ordinal scale, gaining 0 value for the lowest RMSE and 3 value to the highest RMSE, and we'll get the next result. This scale just tells us which one was better than who. In the relative normalization, we want to take into account the distance from the maximum and minimum RMSE values. Using the next equation here below, we can see. And for our specific example, we can see the equation here. And we gain the next scaling, where 0 value is for the best performed camera and 1 is for the worst. And then after we did all the scaling, we sum all the scaled results for each camera. In the next graph, we can see the summed RMSE scaled result for each camera. Each different color represents different combination of camera and algorithm. The first column is for the upper body, and the second column for the lower body. The first row is using the basic normalization, and the second is the relative. And here, we did not use the important features weights, and we gave the same importance for all the features. And we can see that no matter which research focus or which scaling technique we use, the trend is the same. The Z2 millimeter performs the best, then the Z4 millimeter, then the Nuitrack, and at last the MediaPipe. In the next graph, we use important weights. And we can see that for the lower body, the trend stays the same. But for the upper body, at the basic scaling, we can see that the Z4 millimeter outperforms the Z2 millimeter. But at the relative normalization, they're gaining the same results. This is due to the fact that the Z4 millimeters outperform the Z2 millimeters in more features than the Z2 millimeter, but they outperformed in small difference. Now we move to the part of this linear mix model. We use the next model for each feature and each camera and compared the calculated feature from the ground truth to the calculated feature from the camera. And we used wall test to test the coefficient, the beta 1, whether it equals to 1. We want to reject the null hypothesis. So we tested and we looked for the camera that we did not reject the null hypothesis the most. And still here, we gained that 2 millimeter was not rejected in 6 feature from the upper body and 4 feature from the lower body, more than all the other camera and algorithm combination. In our discussion, indirect joint tracking is possible and can give us valuable information about the performance of the cameras and algorithms. And we don't need any synchronization. And the second, the camera performance can vary depending on the research focus. Since we can give different weight to different features, we might have different results. And we found that in the Z camera, the lens choice affects outcomes. Since the Z 2 millimeters has a wider field of view, it's better at close and medium ranges than the Z 4 millimeters. To conclude, we propose a methodology for comparative analysis of different cameras and software tools utilized in skeleton tracking. Our feature-based assessment does not require any synchronization, which is the most important thing here and make it much simpler. And in our case study, we found that for our research focus, the Z2 millimeter outperformed all the cameras in most cases. Thank you for listening. Here's the QR code for the paper. If you would like, I would like to answer and say thank you to all the other people that have been a part of this paper.
Please